I found two ways to writing into it, nothing's happening. So this have any mistakes
I didn't have it until like 5 weeks ago, so I didn't change before, and then I did it on this effective credit. Reading the same.
Why was everyone there? I was like, no. Look, season's like really. Oh, it's fine. Everyone knows it. Most of the not on the lane. Like on the lanes. Yeah. I'm just like, Okay, you have to remember the bottom. There's like. It's like they're.
Right, can you guys hear me online okay?
Yes.
We're hoping there's an stage. Or. That's big. I would think now.
That's the main.
That's good.
Bigger than what it is.
Okay, let's get some annual sign. Location. You might be starting right next to me. Let me see how to do it. Let's be hot, this is small. No, it's again, like. How are the English beds has been run?
Okay, so assessments will be due by tomorrow night. And then I'm going to have the quiz open Tuesday, Wednesday. There won't be any in-person class on Wednesday, so I'll have the modules for module 3 will actually be created. And so there'll be videos that you can watch depending on what you're feeling week in and practice problems in those areas. Any questions about any of that? Feedback, yes.
So when will the quiz begin? Would we typically do Tuesday or Tuesday?
By Wednesday night,
Thank you.
but you can do it, you can start it if most people are used to doing it on Tuesdays. So if that's in your schedule, you can still do it on Tuesday. It'll just be due for sure by Wednesday night. Hopefully, that's a good question. See what my schedule is. By either 2 o'clock, so between 1 and 2, it will be posted, if I can get it done that soon. Otherwise, it will be probably between 4 and 5. So I'll say after 1 o'clock. Maybe I'll say 2 p.m. If it's not posted by 2 p.m., then it will be posted after 4 p.m. All right. Okay. Any, sorry, any questions? Any other questions about that? All right, I apologize for not having material posted yet, but still kind of recovering. So, all right, so far we've talked about AC power. We looked at AC power terminology, and then we looked at actually solving circuits to find the AC power in them. And the topic today we're going to move to is for filters. And so for filters, we need to understand some terminology, just like we did for AC power. So the first terminology is active versus passive filters. So a passive filter, and by the way, these notes are posted on the handouts. I just posted them before class, or right at the beginning of class. So if you want to pull those up, you're welcome to. One question online is the assessments and quiz will be on. So the assessments will be on AC power. So the problems that we already went through, it will look like that. And so will the quiz. So it will be on AC power for the assessments and quiz. All right, so passive filters are when you have passive elements such as resistors, capacitors, inductors. Active filters are when you have an op-amp in there or a transistor or other what we call active devices. All right, the next terminology that you need to understand is low pass, high pass, band pass, and band reject. Not sure why band reject is underlined, so they should all be the same. This refers to what is happening in the frequency range for circuits. So when you have a circuit, it will have a range of frequency that it can work in. And so when we solve the circuits in the S domain for the Laplace, if we change to have S is equal to J omega, we can look at omega as being frequency, even though this is angular frequency, which the units would be radians per second. We can make a plot of what we call a transfer function, which was our output over input. And we can create such plots as this, where it's in going through a range of frequencies from 0 to a high end frequency range. It will have a output value. And so over a range of frequencies, if our graph looks like this, first one, it would be a low pass filter. So it means that everywhere where this is passing until it gets to this is called a minus 3 dB level, or 1 over the square root of 2 times the max value. That would be considered the range that this circuit would operate. So it would operate passing whatever it is through it until that range. And then after that range, we would say it doesn't pass anymore. So basically the output would be close to 0. Yes.
Why is it minus?
That's just a definition. And that's called at that definition is one other terminology we'll get to, which is called the cutoff frequency, which is this omega C. And that again will be a definition. Yeah. So omega C would be that cutoff frequency, or another word for it is corner frequency. Cutoff frequency refers to it when it's in a low pass filter. Corner frequency would be when you're in a high pass situation, meaning that everything in this region is considered off, and then in the pass band, or other word for this is bandwidth of the circuit. This one is the corner frequency. So cutoff frequency, they mean the same thing. It's a 3 dB. Band pass is where it has a range in between. So low pass is meaning everything in the low frequencies to a certain frequency, and then it doesn't pass anymore. High pass is that at low frequencies, it doesn't pass anything till it starts, and then everything above that frequency, it operates. Band pass is a range in between there. And usually for band pass, it's a very narrow range is what you want. So you usually want it to be like at almost one frequency, it will pass, but it's hard to get exactly one frequency. So it'll be somewhere right in between there. So this region in between for band pass would be considered your bandwidth. And then for band reject, you have two regions. So you have the low region, which would be considered one part of the bandwidth, and then the higher region, which would be considered the other part of the bandwidth. So you have two regions for the bandwidth in a band reject. So here you would say the bandwidth for band reject is between 0 and omega C1. And then above omega C2. So this would be considered your bandwidth. For both band pass and band reject, you see that you have two corner frequencies, omega C1 and omega C2. You would consider the first one the corner frequency, and the second one you would say would be the cutoff frequency for band pass. So when it's going up, it's considered a corner frequency. When it's going down, it's considered a cutoff frequency. So here they're opposite, where the cutoff frequency would be going down would be WC1 and going up would be WC2, so corner frequency. These are sometimes used very interchangeably. So sometimes it's not actually accurate. Sometimes they'll be considered a corner frequency, even if it's going down. So you'll hear the terminology for both, and they're very interchangeable. It just means a 3 dB point. Yes, you had a question?
Yes, when you're saying like band pass, does that mean like when the signal would be able to be accepted in the circuit, or?
Yeah, so during that region is where the circuit is considered to operate. So if my output was going to be 1, say M1, M0 was 1. And so when I put an input in, it goes in and I get that same output out because it's multiplied by 1. Let me draw this. So going in, whatever is happening to the circuit is multiplied by M1. So I'm multiplying it by M0. So if I have like an input of V1, output would be M0 V1. So during that region, that is going to be the output. But anytime before this region, so any time before is going to be where we consider it off, which would be 0.7 less than that. So at a frequency less than omega C1, when I put this in, I expect it to still multiply by M0, but what happens is I get, something less than 1. So I might get half of the value. or I might get 0.2 of the value, or I might even get 0 out. So it's just less than it. So it's not always just exactly 0, but it will be less than what I expect. So if I'm measuring on an oscilloscope and I expect it to be 1 as the amplitude, and I'm seeing a half, frequency could be a reason why you're not seeing it correctly. Does that make sense? So during a band reject, you're going to see 1 during 0 to omega C1. And then during omega C1 to omega C2, you should see it way less than 1. And then again, you should see it after omega C2, you should see 1 again. Yes.
So right here on the low pass and high pass, how come like right here it starts with a high voltage while high like a maximum and then it goes to low? And then right here you're starting from low and it goes to high. Doesn't that mean that the bandwidth will pass a high frequency that when it activates, or does it, like, is there ever a case where you want to come below frequency that activates the band?
So how you interpret this is that it will give you out from the circuit because it's not like it's triggering anything. It's just that at certain frequencies, you're going to get a different output here. So if this was a low pass, and for an example, say omega C1 or omega C for the low pass was equal to 10 kilohertz. First off, sorry, this should be frequency. Let me back up for a second, 1 small second. So omega C or omega, you guys remember the conversion to frequency? Yep, it's 2 pi over T, which is the time period or frequency. So 2 pi F is the conversion between radians per second and hertz. And so we know things a lot more familiarly in hertz. So that would be the conversion, is that you would first, the equation itself, when you derive it from the circuit, remember it was in omega, because it's S is equal to J omega. So then you would want to convert it to frequency, which would be omega over 2 pi. So if, say I have 10 kilohertz is my corner frequency of this omega C, and I'm in a low pass, and say M0 is 2, then my output up to 10 kilohertz. So say I put in one kilohertz. My output will be 2V1. At 20 kilohertz though, what will be my output? It will be something way less than 2, right? Could be 1V1 or even like 0.2 V1 or something else that's going to be way less. Because I will be like somewhere over here on this graph instead of in the region where it operates, giving me the output. So does that make more sense? Uh-huh. Correct. Yep. Yep. Okay. All right. So we've defined low pass, high pass, band reject, corner frequency. And then also with this, it's called cutoff frequency. So in general, typically corner frequency means it's going up. Cutoff frequency means that the graph is changing to go down. But again, sometimes you're going to hear those terminology for either direction. So if you hear cutoff or corner, just know that it's about 3 dB less than the main value, which in volts per volts would be 0.7 volts or 1 over the square root of 2. Put that there. 1 over the square root of 2 is 0.7 approximately. Okay, talked about converting from omega to frequency. All right, the other terminology is gain factor. So the gain factor is this M0, which is the magnitude. And if you're in a low pass filter, we call that DC gain. High pass filter, high frequency gain. Band pass filter, we call it the gain factor. So same words for the same thing, which is that peak value of your graph, M0. Resonant frequency. So resonant frequency is what we call for omega naught. So omega naught is the term for resonant frequency, and this is just the frequency when the input impedance is purely real or is purely real. So if you have a complex frequency, you can actually make it real by changing the inductance to equal the capacitance so that those equal 0 for the imaginary part of it. So that is also another place where you'll get it to make it a resonant frequency. Gain roll-off, which is considered SG. Bandwidth I kind of already talked about, and then quality factor Q. So if we look at this, we have these different bandwidths. So B1, B2, and B3. So you can see for each of these, you have a narrow bandwidth for B1, B2 is wider, and B3 is the widest. So you would consider for a bandwidth 3, which in this case is what kind of a graph is this? Which type of filter? Yep, so band pass. So this is for the band pass specifically. So for band pass, if you have a wide one, you're considered a low selectivity or poor selectivity where your Q quality factor will be low. So you can see at the top one, Q is 2. For as it gets to be more and more narrow, the Q gets higher. So a high quality factor means that you have a high selectivity of trying to get that to be almost a one single value. Is there a question? Yeah. Sorry, what? What the voltage?
What filters actually are.
What do you mean? I guess.
Oh, I mean, what the filters do and make it graph do that.
Oh, we're gonna look at a little bit of it. And then I'm trying to remember which class it is. There is another higher level class that goes into all types of filters. I just can't remember the name of it. Which one? Signals and systems will get in there, and then there's another one after signals and systems. So ECE 3500 talks more about some filtering, and then you talk about them in that capacity, usually more like with a digital filter. And so you're going to be programming filters in algorithms. And then trying to remember there's one after 3110 where you actually can look into making the filters in hardware. I just can't remember the name. So there's two different kind of sides. If you go into the signals and systems, they'll talk about filter algorithms in more of a programming side. And then there's one in hardware that's after 3110. It's like advanced analog systems, I think. So, yeah. All right. So with this, understand Q quality factor, higher value is more ideal. And then SG is the roll-off rate. SG. No, I missed putting SG on here. So let me talk about the rest of the quality factors. So for actually, which one would this graph be here? It is a low pass. Good job. So for a low pass, you would consider Q is going to be that peak here. It has moderate resonance. This is a weak resonance. So it's talking more about the resonance, and then ideal would look like this one. So for a low pass, we actually don't want resonance. So we want a low quality factor there. For this graph here, what's this one? High pass, low pass, band reject. Thank you, high pass. So high pass. And it is not a band reject. That one was a low pass. Oh, at the top. No, this would be a pass band instead of a band reject. So the band reject goes down. So this one is the band reject. So high pass, again, you don't want a high resonance for that one. And then band reject, you again want a very narrow region where you're just rejecting almost a single frequency. And so ideally the high Q is what you want on that one too. Yes,
How do we calculate the Q value exactly?
I'll go into that. That's easier seen by. So I'm gonna just jump to looking at the circuit and finding these values. So we want to find out from this what type of a circuit this filter is. Is it a band pass or band reject? And so what we want to know and be able to find for that is what we call a transfer function, which is going to be the output in omega over the input of omega. So we're going to go back to, you can either, I like to solve these with S first and then just plug in S is equal to J omega. But you can also just start off with J omega and solve it. So we need to first convert all of the elements to either SL or J omega L, and then 1 over CS or 1 over CJ omega. So how would we solve this? How? Yep, so you can treat these, once you have this, you can just treat these as putting all three of those in parallel, or you can do a node voltage, a V naught. As you all know, I kind of like node voltage, so. What is this branch going to be? What's this node? Yep, so this node is VO. What's this node? VI, correct. So what's that current?
Oh, PO minus VI or 10. PO over the PO. FL, yeah.
Yep. So if I use the Thevenin, I would take R2 in parallel with SL plus 1 over CS plus the R3, combine all of those, and then it's a voltage divider. So it will give you the same equations, whichever one you prefer. So to make this have the same denominator, I'm going to bring the CS. So that combines it into one denominator. And then the CS goes to the top, so it's going to be CS over SLCS plus 1. VI. Sorry, I thought I had this in numbers, but it's not finding it in numbers. Okay. So So we want to get a common denominator here. So SLCS plus 1. And then 3. So we want 30K SLCS plus 1. Becomes 1K. L and C. L was 40 nano and C was 10 nano. +3. S squared, okay. S squared. Yes. This is not. Heavens, I can't put these in my calculator. 40 nano times 10 nano times 3. Okay. 1.2 15 s squared plus 3. Nano times 10 nano. There we go. That's 2. Okay. So So if we put in S equals J omega. Why are we? No, that's okay. So to plot it over omega, to look at the plot, to see what form it has, you would put omega, or you need J omega. So you need omega in there to plot it. Give me time. Okay, this is not letting me do this. Bodhi is one of the functions of the control toolbox, so must not have it on this one. All right, so if you were to plot this, you're gonna see that it is a band reject. Graph this. Yeah, so graph this. Or, in S. So you treat this as a function. It's the output over the input, which is a transfer function. And then you graph this with the variable of omega. And so your X value is kind of omega. And so it will be a graph of omega. So it'll be a graph with omega in your X axis.
I don't we divide VI by VO.
Why do you?
Like, why don't we divide VI by VO like the opposite, right? We're dividing VO by VI. We're dividing VI by VO.
So this is the definition of transfer function. It's always the output over the input. And the reason you want that is because this ends up being at one specific frequency, it's going to be a value. So say it's a value of 20. You want to know that if you put in an input, what will be your output? And so that's why it's output over input. So your goal is typically, what is my output for a given input? So if you define that transfer function as output over input, I give you an input, say it's 1. And say this function ends up being 20, then your output will be 20, right? You just multiply the 20 times 1. If your input's 2 and your outputs and your gain, the function gives you a value of 20 and your input is 2, you would get 40 out. So that will help you define, like, if I know what my input is, my output can be defined. If you graph it the other way, you can't, that's not going to give you that information. Does that make sense? All right, so omega naught for a band reject is going to look like 1 over the square root of LC. There's a big derivation in the book if you want to go through that. If you remember from our LC circuits, when we did those, it was always 1 over square root of LC. So it does come from the derivation of putting the real and the imaginary, or not the real, the SL equal to 1 over CS. So we want SL to equal over J omega naught L. Going with this, and then solving this for omega naught. We get 1 over, oh, sorry, this is, what did I do? Omega naught C, J omega naught C, yeah. Omega naught squared, and then you get J squared LC. Did I do that right? J squared LC. Oh, yeah, I don't have J's in here, that's why. So all of this is the J portion. And so we want omega naught L to equal 1 over omega naught C. So then this becomes omega naught is 1 over LC. Square root. So that's where that comes from. So this is the resonant frequency omega naught. So in this case, it's just going to be the square root of 1 over 40 nano times 10 nano. Square root button. Gonna be 50, 1, 2, 3, 4, 5, 6. So omega C1 and omega C2. Are going to be when you take the quadratic of this. So taking the quadratic of this gives that value or those two values. So your bandwidth is going to be the difference between the two. which is pretty much approximately 150 gig. And then the quality factor is going to be the resonant frequency over your bandwidth. So 50 mega radians per second over 150 gigaradians per second equal 1/3 milli. So is that good or bad value? It's what? It's what? It's very bad. So for a band reject or a band pass, we want that quality factor to be really high, meaning that it's a very narrow width. But if we have 150 gigaradians per second as our bandwidth, that's really, really wide. So it's not very selective would be, and so yes, very bad. Poor value there. Yes, quadratic formula of this. So just taking the quadratic formula and solving for omegas.
That's the factor.
So this was the denominator. So taking that and finding the omegas as far as the root solutions of those are going to give us those two values.
So is it always the denominator or?
Yes. Yeah. All right. Let's see. All right, this is all I had for today. So are there any questions? Okay, we're going to end early. And so again, no class in person on Wednesday or online. It's going to just be on your own time to go through the material that I'll post so that you guys can work through other problems. When we get back, we're going to talk about Fourier series. So if you want to go back and refresh yourself, if you've seen Fourier series in your math class. Otherwise, I'll be posting some material online about Fourier series. So do watch that and kind of be ready to work through some Fourier series going forward. All right. Have a great Thanksgiving.
So, how did you do it? Omega 1, Omega 16. I mean, they're like the roots, but like, how do you conquer the by
should be this. So this is your A. This is your B. And this is your C.
I see. So like your term is the variable. The variable.
So the J squared goes to a -1. And then the J, yeah, I am. Let me think about that one, because that has still a J in the middle one.
Shouldn't AG like 1.3 8 to negative 15 plus 8 e to the negative 16.